everyone, and welcome to today's lesson. Today we're going to talk about finding the key features of our rational functions by using their equations. First thing we're going to talk about are the horizontal asymptotes. And our horizontal asymptotes are our horizontal lines that our graph approaches as our inputs increase or decrease without bounds. So essentially, as the x's go to either infinity or negative infinity, they're going to approach these horizontal asymptotes if they exist. And what we're going to notice is these, again, help describe that end behavior, and the decision on if they exist or not is going to be based on the degree of the top versus the degree of the bottom. So what happens if the degree of the top is equal? So the degree of the numerator equals the degree of the denominator. Then what's going to happen is the ratio of the leading coefficients is going to end up being the equation of our horizontal asymptote. So notice our leading coefficients are 3 and 1. So 3 over 1, or y equals 3, would be the equation of our horizontal asymptote. In the second one, we have a degree in the numerator that is less than the degree of the denominator. So notice this is degree 1 versus degree 2. So when that happens, our horizontal asymptote is going to be at y equals 0. When the degree of the numerator is bigger than the degree of the denominator, what's going to happen is there is no horizontal asymptote. So you would just say there is none. Our y-intercepts are going to be found when we plug in 0 for our x value and simplify. So for instance, on this first one, if I'm plugging in 0 for x, this is going to cancel out to be 0, and I have 2 on the numerator. Then I would have 0 squared times 4 times 0 minus 5. Again, these both cancel out to be 0. So we have 2 over negative 5. So you'd have your y-intercept at 0, comma, negative 2/5, or negative 0.4. And the next one, again, if you plug in 0 for x, essentially what's going to happen is 4 times 0 is just 0. So we have 2, and then 0 squared plus 4 times 0. Again, on this one, we end up with 0, comma, negative 2/5 again. And then last but not least, in this unfactored one, if we plug in 0 for all of our x values, on the numerator, we would end up with negative 2 times 3. In the denominator, we have negative 1 times negative 2 times negative 5. So negative 6 over negative 10 ends up being positive 3 over 5, or 0.6. So 0, comma, 3/5 would be our y-intercept. Our vertical asymptotes are going to be vertical lines that our graph approaches but does not cross over. Again, those are vertical lines on our graph. So to find our vertical asymptotes, we are going to want to factor both the numerator and the denominator, and then anything that does not cancel out in the denominator, you're going to set equal to 0 to find the vertical asymptote. So for instance, on the first one, we have nothing to factor to simplify. We have x minus 1 in the denominator that we could set equal to 0. So x equals 1 would be our vertical asymptote. In the second one, we have 2 pieces that could be set equal to 0 from the denominator. X plus 9 equals 0. So x equals negative 9 would be a 0. And then x minus 4 equals 0. So x equals 4 would also be, not a 0, a vertical asymptote. Our wholes then are going to occur when we factor the numerator and the denominator, and these are the pieces that do cancel out. So any of the pieces where they cancel is going to be the whole, and then to plug back in to find the y value, you will plug that x value back in. So for instance, we see that x plus 3 can cancel in this particular function, so we know the x value of negative 3 is going to be the location of our whole. But again, our wholes are x comma y, coordinate points. So to get this y value, what we would do is we would plug negative 3 back into this piece that we have left over after we cancel out our pieces. So we would have negative 3 over negative 1. So positive 3 would be the location of our hole. So negative 3, comma 3. On the next one, if we factor, we end up with x squared minus 16 being a difference of 2 squares. So x minus 4 and x plus 4 would be 2 factors. And then we have x plus 4 as another factor there as well. This time, these are going to cancel out the x plus 4s. So we know we have a hole at the x value of negative 4 if we set that equal to 0. And if we plug negative 4 back into our piece that we got after we simplified, we end up with negative 4 minus 4 more, which is negative 8 over 2. So negative 4 is also going to be the y value this time of our hole. So x value of negative 4, y value of negative 4 would be the location of our hole. All right, last piece here to look at are our x-intercepts. And these are our real zeros that we see on the graph. So again, these are the ones that you would actually be able to see plotted in our pictures. So for the x-intercepts, this is going to be where we set the numerator equal to 0 that did not cancel out to be a hole. So in this case, if we look, we have nothing that's going to cancel out. If this is going to be imaginaries down here, so we can't factor that. So what we do is we set, again, that numerator piece equal to 0, and we have x equals negative 5 as the value of our x-intercept, or real 0. In the second example, if we factor, we would have x plus 6 and x plus 1 in the top. On the bottom, we would have x minus 4 and x minus 6. So notice we have no holes. So to find our x-intercepts, again, we would set these two pieces equal to 0. We have x equals negative 6 and x equals negative 1. So negative 6 comma 0 and negative 1 comma 0 are our two x-intercepts. Finally, we notice on the last example that we have a hole at x plus 2. So the only piece left to set equal to 0 in that numerator is negative 3. So negative 3 comma 0 would be our x-intercept on that one. Now our overall end behavior of the graph as x goes to infinity and as x goes to negative infinity is actually based on what we originally talked about at the beginning, and that is our horizontal asymptotes. So in order to find our overall end behavior of our graphs, we want to make sure that we look at the horizontal asymptotes. So on this first one, notice the 2 degrees match here. They're both degree 2. So y equals 1 over 1, aka 1, is our horizontal asymptote, which means as x's approach infinity and negative infinity, they're going to converge towards that y value of 1. And the second one, we also have another where our degrees match. Both are to the first power. So y equals 2 is our horizontal asymptote, which means each of these are going to converge to y equals 2. On our third example, notice the degree of the numerator is less than the degree of the denominator. So we would have y equals 0 as our horizontal asymptote, but we also have a vertical shift up 7 from that. So really y equals 7 ends up being our horizontal asymptote. So again, 7 is where we would converge to. And then last but not least, on our final example, we again have another degree of the denominator bigger problem. So y equals 0. However, this time we are shifting down 5 units. So y equals negative 5 ends up being our horizontal asymptote and where our graphs will ultimately converge to. So if we take a look at that last example, for instance, just to see again in like picture format, looking at a graph, how this works. Notice as we look at this graph, we converge through y equals -5, this horizontal line here, as we go to negative infinity or as our x's go to positive infinity. Thanks everyone for watching. We'll work way more with these different key features in class.